All right, let's finish up acids and bases. So this last video is going to look at the second half of the um, notes on acids and bases. We're going to start with slide number 23. Now, this video is going to cover a couple different topics, so we are going to segue between different ideas here, but this is going to help us finish up acids and bases. So let's start by looking at the behavior of acids and bases as electrolytes in solution. So what is an electrolyte? An electrolyte is something that conducts electrical current in solution. It's pretty simple. Any of our ionic compounds that will dissociate in solution will conduct electricity. And when we learned about ionic compounds earlier in the year, you'll remember that one of their 7 characteristics was that they are good conductors of electricity in solution. That's because, or that's another way to say that they are electrolytes. Now, if something dissociates 100%, so all of the ionic molecules break apart in solution into their ions, then we call that a strong electrolyte. If it's anything less than 100%, it's a weak electrolyte. And usually, if something doesn't break apart all the way, it's not going to hardly break apart at all. And so it's usually somewhere like less than 5% dissociated. Now, strong acids, because acids are ionically bonded, fall into our discussion of electrolytes. And a strong acid will always dissociate completely. That's what the definition of a strong acid is. Now, there are only 3 binary acids that are strong acids. Just memorize them because any other binary acid is a weak acid. And they are HCl, Hbr, and Hi. Now, those of you who are paying attention here may realize that all of those are from the halogen family. And so you might be thinking, well, wait a minute here. The halogen family starts with fluorine, and then we have chlorine, and then we have bromine, and then we have iodine. So wouldn't HF, right? Why is HF equals a weak acid? A really good question there. Like, why is that true? Well, there's actually a pretty simple definition for that. We know that electronegativity, wow, that's like the worst. Hold on. Oh man, that was terrible. All right. We know that electronegativity increases up and to the right, and we know that the highest electronegativity is fluorine. And what is electronegativity? Remind yourself of that, right? Electronegativity is the tendency for an atom to attract electrons to itself in a bond. And so in HF, because fluorine is so electronegative, this right here is really tight. It's really tightly held. And so when you put it into solution, water is not able to break it apart into H+, so you don't get H+ and F- at 100%. It just doesn't do it. And so HF is a weak acid because the definition of a strong acid is it has to break apart 100%. Fluorine is too electronegative, so HF doesn't completely dissociate, so it's a weak acid. Now, don't confuse weak acids with reactivity of acids because hydrofluoric acid is an extraordinarily reactive acid. You can't store it in glass because it will etch the glass. So it's a really reactive acid. That's not what strong and weak acid is referring to. We're just quantifying or qualitatively describing, rather, if something will completely dissociate or not. And when it comes to binary acids, there's only 3 strong acids, HCl, HBr, and Hi. All other binary acids are weak. So if you got a question, say, hey, H2S, hydrosulfuric acid, is that strong or weak? Well, it's not HCl, HBr, Hi, so it's weak. That's what we want to be able to do with that piece of information. Now, for our oxyacids, we have a little bit different of a rule. And it's pretty simple. If the number of oxygen atoms exceed the number of hydrogen atoms by 2 or more, the acid is strong. All right, let's see what that looks like. HNO3. Well, how many oxygens? O equals 3. How many hydrogens? Equals 1. 3 minus 1 is 2. So strong. There we go. How about H2SO4? All right, 4 oxygens minus 2 hydrogens equals 2. Strong. If it's 2 or more, we're strong. All right, that's what we're talking about there. Let's think about H2. Oh, nope. Let's see, would that work? Oh, I know we got a weak one here in a minute. We'll look at a weak one in a second. When we're talking about weak dissociation, we still get an equilibrium. All right. And so another way we might be able to spot a weak acid is if you see this symbol, right? Because that means equilibrium. Where if I want to write the strong dissociation, I would say something like this: HCl plus H2O yields, so an arrow in one direction, hydronium and Cl minus, right? So that tells me strong. This tells me I have a weak acid, right? Little rule of thumb there. So let's talk about strong bases. Strong bases have to completely dissociate in solution. Hydroxides made from the metals in group 1 or 2 are strong bases. So if the metal is an alkali metal or an alkaline earth metal, you have a strong basis. You have a strong base. Otherwise, it's a weak base, right? So any of the bases with, say, transition metals, we're going to classify them as weak bases. With the lanthanides or the actinides, weak bases. The only strong bases are going to come from group 1 or group 2. Now, there are some other bases that are weak bases that are not hydroxides. Just make sure that you're aware of that. So like ammonia is a weak base, all right? That's one that we should probably commit to memory. Ammonia, which is NH3, just giving you a little hint here for something to come, is a weak base. All right, there we go. Make sure you know that. Now, just like acids, weak dissociation results in equilibrium. So if I see that, the equilibrium symbol, which we looked at in when we did kinetics, if we see that equilibrium symbol, then we know, hey, we got a weak base, or we have a weak acid. If we just see a yield arrow, that is a strong base or a strong acid. So let's do some practice problems. HF, all right, it's binary. Is it HCl, Hbr, or Hi? Nope, so it's weak. H2S, same thought. It's binary. It's not hydrochloric, hydrobromic, or hydroiodic, so it's weak. H2SO4, all right, it's oxy. So do we have 2 or more oxygens than hydrogens? Well, 4 oxygens minus 2 hydrogens. 4 minus 2 is 2. 2 or more is strong. That's the H2CO3. All right, here we go. I have 3 oxygens. I have 2 hydrogens. That's 1. 1 is less than 2, so that's a weak acid. Iron hydroxide. All right, iron is not an alkaline metal, alkaline earth metal, or an alkali metal, so it must be weak. There we go. See, calcium hydroxide. Well, calcium is a group 2 compound, right? So it must be strong. Chromic acid. All right, I go to my polyatomic ion sheet. I go chromic must come from chromate. Chromate is CrO4. H2 out front, 4 minus 2, because it's an oxyacid. I want to know oxygens compared to hydrogens. I have 2 or more, so it must be strong. Phosphorus acid. All right, ORUS, the OUS at the end, the US, tells me I have phosphite as my starting compound. So that's H3PO3. 3 minus 3 is 0, so that's a weak acid. It's not 2 or more. Acetic acid. All right, I'm coming from acetate, so I write my acid there. I have 2 oxygens, and I have 4 hydrogens. So I actually get 2 minus 4, that's negative 2. So it's a very weak acid. Hydroselenic. Hydro tells me, hey, that's a binary compound. Binary only has 3 strong, right? HCl, Hbr, Hi. It's not one of those 3, so it must be weak. So that's how we define weak and strong acids and bases. Let's look at something else. Anhydrides. So the word anhydrous means without water. An anhydride is an acid or base that has had the water removed. Our nonmetal oxides are going to form acidic anhydrides, and our our metal oxides are going to be forming basic anhydrides. So over here I have a nonmetal oxide. What do I mean by nonmetal oxide? Well, I have a nonmetal bonded to oxygen, and when I add water to it, it makes an acid. In the case of the metal oxide, I have a metal bonded to oxygen. When I add water to it, right, because anhydrous means without water. So if I want to undo an anhydride, I have to add water to it. Then I'm going to get a base, right, the OH there on the right side. Let's do some practice problems with these. Tell me if this thing is going to make an acid or a base. So Li2O. Do these as we go, right? So on the right, we're going to write acid or base here. Okay. Let's do the first one together. Lithium is a metal, and so a metal is going to make a basic anhydride, right? So lithium oxide, I would write right here, I would write basic. All right, let's look at the second one. Magnesium oxide. All right, I have a metal oxide. Must be a basic anhydride. CO2, all right, that's a nonmetal. So this is going to make an acidic anhydride. All right, you do the rest. Here we go. K2O, what's K? Write it down. What do you think it is, acid or base? It's a metal, so it must be basic. Selenium oxide, dioxide here. This is a nonmetal and an oxygen, a nonmetal oxide, so it must be acidic. All right, Cl2O7. Well, Cl is a nonmetal, and so we would expect to make an acid. All right, this is going to make an acid, and this is going to make a basic anhydride. All right, so I'm just looking at what it's bonded to. So if I have a metal oxide, I can predict that I'll have a basic anhydride. And obviously, if I have a nonmetal oxide, I can predict I have an acidic anhydride. All right, so let's actually go forth and predict the formula, right? Go forth and write formulas. So lithium, this would be lithium oxide. What is the basic formula it's going to make? Well, when I add water to that, I'm going to get lithium hydroxide. That's definitely a base. All right. How about magnesium hydroxide? Because I know if I'm making a basic anhydride, I'm going to get a hydroxide out of it. So I know that magnesium is +2. I know that OH is -1. So I know that when I put this MgO into water, I'm going to bond these two things together. So I'm going to get, when I cross my charges, MgOH2. All right, CO2 makes an acidic anhydride, right? That's the acid that I'm going to make from that acidic anhydride. So I know that I have hydrogen, it's +1. All right, my CO2 right there. All right, that's probably not going to work out. So what do we know that has CO2 in it that when I add a water to it could come up with a new compound? Well, think about it more like this. I'm going to take CO2 and I'm going to add H2O. Well, that's going to give me H2CO3. And that's going to be my acid. And that's a clever little trick there, right? When you take an anhydride and you add water to it, you're literally adding water to the compound. So there we go. K2O is basic. So I'm going to end up with KOH. K is +1, OH is -1. SeO2, well, I'm going to get HSeO3. Let's see if that works out. I have SeO2. This is the acid one, so I'm going to get H2O. So I'm going to get H2SeO3. There it is. Cl2O7. Now, this one is interesting because the answer is going to be H2Cl2O8. There we go. But what do we know about ionic compounds? We need to reduce them. And acids are ionic compounds. So I can reduce all of this by a factor of 2. So I would say HClO4. And that would be my answer there. That's a tough one. Let's do some more practice problems. All right. I'm going to give you BaOH2. You tell me the anhydride. Well, I'm going to remove a water. So let's kind of look at what we have here. We have Ba with 2 O's. And we have 2 H's, right? That's BaOH2. I'm going to take away an H and, Ba O2, H2. I'm going to take away H2O, right? So two H's and an O. So that's going to leave me with barium. 2 minus 1 is 1. That cancels out. So just BaO. I'm taking a water away. That's what anhydride means. All right, HiO4. Well, I can't actually take two hydrogens from this. So I need to double everything. So I'm going to say HiO4. I can't take away, right? I don't have two hydrogens, right? I'm missing it. So I'm going to multiply everything by 2. I'm going to get H2, I2, O8. And now I'm going to take away H2O. And I'm going to be left with I2O7. And there's my anhydride. All right. H6TeO6. Well, that's pretty simple. All right, I need to take away some waters. So let's take away some waters. TeO3. Look at there. All right, why did I take away 3 waters just now? Well, remember with your anhydride, you have to get rid of all those hydrogens. So if I'm going to take away 6 hydrogens, I have to take away 3 waters in order to get TeO3. How about aluminum hydroxide? What's that going to be? Well, AlOH3 is going to come from an aluminum oxide. And in order to get an aluminum oxide, I just need to cross my normal charges. So aluminum's plus 3, oxygen's minus 2. So I'm going to get Al2O3. There it is. Zinc hydroxide, same thing. We know zinc is always plus 2. That's a rule. Oxygen's minus 2. So I'm going to get ZnO. There we go. Now, anhydrides are pretty complicated. It's good to know about them. We might use them in the lab, but I'm not going to give you any major brain busters on these guys. All right, switching gears again. Neutralization reactions. What is a neutralization reaction? Well, a neutralization reaction is something we learned about when we talked about the 6 reaction types. And the thing I like about acids and bases is it pulls things that we've learned all year and it kind of puts them together. So a neutralization reaction is when an Arrhenius acid and an Arrhenius base react and they form a salt and water. So here's a great example of a neutralization reaction. I have hydrochloric acid plus Li, or sodium hydroxide, is forming sodium chloride and HOH, right? That's H2O. The salt is a combination of the cation from the base and the anion from the acid. So the cation on the base is sodium here. It's Na plus 1. The anion from the acid is the nonmetal. It's chlorine minus 1. So Na plus 1, Cl minus 1, make sodium chloride. Now look what I'm left with. HOH, which is going to form H2O, right? There's my water. Pretty simple stuff. So let's predict some of these. HNO3 and KOH. Right. This is an Arrhenius acid with an Arrhenius base. So I know that the H and the OH is going to produce water. And that's going to leave me with a metal and a nonmetal. We know that K is a plus 1 and O3 is a minus 1. So my salt is KNO3. And obviously I make water with it. Try this one. Hbr and Ammonium Hydroxides. Take a minute. You know you're going to make water. What's the other thing you're going to make? Well, cross the charges, right? Here's my metal species. Here's my nonmetal. We know that NH4 is plus 1. We know that bromine is a halogen. It's minus 1. So NH4Br and HOH, right? Water. Now, just for the record, don't write this on an answer. Write H2O. I'm really just doing that so you can see we're making water. All right, let's try number 3. I've got H3PO4 and I have calcium hydroxide. All right. Well, we know we're going to make water, and that leaves me with calcium and phosphate. Cross the charges. Calcium is a plus 2 metal. Phosphate, because we memorized it, is PO4 minus 3. So I'm going to get Ca3, PO4 in parentheses 2, and I'm going to make water with it. Try this one with words. All right, this is a tougher one. Sulfurous acid and lithium hydroxide. What's that going to make? Well, probably be useful to convert this over into a formula. So sulfurous acid, we know that OUS comes from ite. So we have sulfite, right? we know that sulfate is SO4 minus 2, right? That would be sulfate. So sulfite must be SO3 minus 2. So H plus 1 and SO3 minus 2. Our acid here is going to be H2SO3. Lithium hydroxide is way easier, right? Lithium is plus 1, hydroxide is minus 1, so we would get LiOH. So now we have those. Now it's a whole lot easier to write out our new answer. So we know H and OH is going to form water. So we have lithium, which is plus 1. We have sulfite, which is SO3 minus 2. So that's going to give us lithium sulfite, which is Li2SO3. There we go. Lithium, sulfite, and water. Hopefully that makes sense, all right, as far as predicting those products and all. Now, it is a good idea to make sure that we balance these when we're done, right? This is definitely not balanced. I have 3 calciums on the right and 1 on the left, all right? But, you guys know how to balance, so we're not going to jump into that right now. Let's look at the pH scale. So the pH scale compares the concentration of hydrogen to the concentration of hydroxide. And when the concentration of hydrogen ions is greater than the concentration of hydroxide, we say the solution is acidic. If it's the other way around, we say the solution is basic. So let's look at these. Which is more acidic? 3 molar hydrochloric acid or 3 molar hydrobromic acid? Well, in order to look at this, we would have to do some math. And so let's look at another one. 6.8 times 10 to the negative 5th molar hydrosulfuric acid, or 3.2 times 10 to the negative 2 molar hydrofluoric acid. See, if you know the pH, then you can tell me that answer. But if you don't know how to go from molarity to pH, you might be in trouble. So let's figure out how to do that. Well, here's the pH scale. It's a formula. pH is the negative log of the concentration of hydronium. pH scale runs from 0 to 14. All right. Now, the higher the pH, okay, the more basic the solution. The lower the pH, the more acidic the solution is. If you have a pH of 7, we have neutral. Now, since pH compares hydronium to OH, that also means there's a pOH scale, which just runs in reverse. So on the pOH scale, acids are between 14 and 7, bases are between 0 and 7. We're really not going to use the pOH scale for anything, but it is useful to know it exists. If you take AP chemistry, we'll definitely use the pOH scale. Now, just so you know, the pH scale was invented by a guy named Soren Sorensen. It was invented in 1909. And the higher the pH, he said, obviously, again, the higher the ion concentration of hydrogen, and the vice versa. The scale doesn't have a fixed limit, though. It doesn't only go from 0 to 14. It can actually, you can have a pH lower than 0, which we call a superacid. Concentrated hydrochloric acid actually has a pH about -1. And sodium hydroxide can actually go up to 15, and that would be a super base. Anything outside of the regular 0 to 14, we just add super in front of. So superacid or super base is just something that's outside the pH scale of 0 to 14. Now, something cool about the pH and the pOH scale that we could use is this fact. pH plus pOH equals 14. So if someone gives you the pH in a problem, you can find the pOH by just doing 14 minus pH. If you know the pOH, you can find the pH, right? 14 minus pOH is going to give you the pH because they have to add together to get 14. So there we go. Let's calculate some pH. So in order to calculate pH, you got to know the concentration of hydronium ions in moles per liter, which is molarity. We've already done that. So the pH is the negative log of hydronium, and we can use hydronium or H plus interchangeably, right? So either one works. And just so we're refreshing this logarithm idea, a logarithm of a number is the exponent when that number is expressed as a power of the number of 10. So 3.78 is the same thing as 1 times 10 to the 0.5775. So that means the log of 3.78 is 0.5775. That's the relationship there. We graph a logarithm, we get a logarithmic curve. And if you compare the concentration of hydroxide to the concentration of hydronium at the point where they are the same, which is right here where they equal each other, right? That is the pH of 7. And look at there, 1 times 10 to the negative 7th, all right? Log of 1 times 10 to the negative 7, or the negative log of 1 times 10 to the negative 7, because that's what pH is, right? pH equals negative log of the concentration of H3O plus. Well, the negative log of 1 times 10 to the negative 7th is 7, right there. That's the point where they are equal. So that's why 7 is neutral. Let's do one of these. Find the pH of a 0.0025 molar hydrochloric acid solution. The HCl is a strong acid, and it's completely ionized in water. That means the hydronium concentration is the same as the molarity, so it's 0.0025. So we take our calculator and we put negative log of 0.0025. That's negative 2.6. So what's the pH? 2.6. All right, that's cake. Easy stuff. Let's look at example 2. It says, what is the hydronium ion concentration in a solution that has a pH of 8.34? All right, so now we need to solve this equation for the concentration of H3O+. But we have a log in the way. Well, fortunately, we've already solved equations with logarithms this year when we did the half-life equation, which has a logarithm in it. So we're going to use the anti-log. So let's flip the negative. Let's get it out of the way. So we move it from the left to the, or from the right to the left. Then we're going to take the anti-log or the inverse log. We're going to set both sides as an exponent of 10. So that means the concentration of hydronium equals 10 to the negative 8.34. And that cancels out the logarithm function. Punch that into your calculator and it gives you 4.57 times 10 to the negative 9th. That's the molarity. That's the concentration of hydrogen ions. Now, how do we measure pH? Well, the easiest thing to do is use a pH meter. It's going to give you a digital readout that just says, hey, the pH is whatever it is, 1.2 or 15, whatever it is. The way that it does this is it uses electrical conductivity, right? Because remember, the more dissociation you have, the greater the electrical conductivity is. Now, we can also use indicators. And indicators are things that change color over some given pH range. And you can read more about those on page 658. But we're going to talk about them when we talk about titrations. So what is more acidic, pH of 2 or pH of 3? And by how much? Well, obviously we know that the pH of 2 is more acidic. But what you may not know is it's more acidic by a factor of 10 because pH is a logarithmic scale. A pH of 2 is 10 times more acidic than a pH of 3. Well, let's measure pH when we go from 2 to 4. So let's have a pH. Let's draw it as a number line. Right. We'll say here's a pH of 1, 2, 3, 4, 5, 6, and there's neutral. So let's start at a pH of 1 and compare that to a pH of 2. Well, we would say that a pH of 2 is 10 times more acidic than a pH of 3, right? That's what our question asks us right here. So that means between 1 and 2 would be 10 times more acidic. Between one step, you always have times 10. But that means between 2 and 3 is also times 10. And between 3 and 4 is also times 10. So if I wanted to compare 1 to, say, 4, well, 10 times 10 is 100, and 100 times 10 is 1,000. So a pH of 1 is 1,000 times more acidic than a pH of 4. And if you keep going, right, times 10, oh, what happened? Times 10, times 10, times 10, right? 10 times 10 is 100, times 10 is 1,000, 10,000, 100,000, right? So between, 6 and 1, you have 100,000 times more acidity. So that is the pH scale, right? That's how we measure it, all those good things. Now, some things you might be familiar with on the pH scale include things like battery acid, which has a pH of 1, vinegar, which has a pH of 3. So, like, again, how much more acidic is battery acid than vinegar? Why can you drink vinegar, but you can't drink battery acid? Well, times 10 times 10, from 1 to 3, battery acid is 100 times more acidic than vinegar, right? Milk is actually a little bit on the acidic scale. It's between 6 and 7. It's always kind of confuses people because they're like, hey, milk of magnesia, right, is a base. Well, yeah, but that's not milk. Okay. Baking soda has a pH of about 8.5. Seawater has a pH of about 9. And this is really important. All right. We're going to talk about it on the next slide. Something else that's kind of interesting, acid rain can range in pH anywhere from 5 to 1. Obviously, an acid rain event with a pH of 1 would be very bad for an environment, right? Because at a pH between 3 and 4, all your adult fish in an ecosystem will die. At a pH between 4 and 5, your fish eggs don't hatch, so we can impact our fish populations. And the normal range of a stream is between 6 and 8. And so acid rain falling on a stream can lower the pH. If it lowers it too much, you don't have any more fish, right? That makes sense. In the ocean, all right, carbon dioxide emissions, right, which we usually equate to a conversation with global warming, also does something else. It can do what's called ocean acidification. So as the concentration of CO2 in the atmosphere increases, right, then you have more of a tendency for that CO2 to dissolve in the ocean. When you dissolve CO2 in the ocean, right, we just talked about the fact that CO2 is a nonmetal. It forms an acidic anhydride when you add it to water, makes carbonic acid. Carbonic acid interacts with bicarbonate, which is formed by carbonate and hydrogen ions in the water. Well, why is bicarbonate and carbonate? What does that matter? Well, all of the things that form calcium carbonate shells in the ocean rely on the concentration of carbonate in the water. When you have ocean acidification occurring, everything in this equation starts to shift and you lose carbonate in the ocean. And so with fewer carbonate ions in the ocean, you can get malformed shells in these creatures. You have reef death because the coral reefs are formed from calcium carbonate shells. And both of those things are obviously bad overall because the reef is a nursery for many of the fish that live in the ocean, right? So if you start to lose and bleach your reefs, then you can affect the fish population down the road, which many of us may rely on for food around the world. So putting CO2 in the atmosphere not only increases global temperatures, but it also can lead to ocean acidification, which is not a good thing. Speaking of acid rain, where does acid rain come from? Well, nitrogen monoxide, nitrogen dioxide, carbon dioxide, sulfur dioxide, and sulfite are all, or sulfur trioxide rather, it doesn't have the charge, so it's not sulfite, are all gases that are produced as pollutants. All of them are non-metal oxides, and we know that non-metal oxides are acidic anhydrides. So when you mix these non-metal oxides, these pollutants, with rainwater, you get an acidic solution. And so sulfite, for example, when you mix it with rain, right, because rainwater, you get sulfuric acid in solution. And that sulfuric acid then falls on the ecosystems, right? And that can affect them. It can also affect architecture, right? If you have limestone construction on your, older buildings, like say the Notre Dame or, some like Canterbury, the carvings around Canterbury Abbey or whatever it is there in England, the acid rain can, I'm not a historian of architecture, obviously. The acid rain, though, can eat away those limestone structures, and, we lose some of our historical heritage there. All right, we're almost done. Last thing, I know this is a long video. You need to pause it, all right, as we're breaking each of these topics up. Give your brain a break. But let's talk about titrations. So I know last week, or not last week, last week we talked about molarity and dilution. We talked about a titration. So let's just review that since we're in the acid-base section. A titration is a method that we use to determine the concentration of an unknown. All right, we use a standard, a known solution of known concentration. We have an end point, which is the point where we want to stop our titration. We'll talk more about that in a minute. And we often use an indicator, we have to use an indicator, in order to determine when our pH is changing by monitoring the color change. Let's do another titration problem. I know you did one last week, but let's do this one. So it says 30.84 milliliters of 0.128 molar sodium hydroxide is required to reach the phenolphthalein endpoint in titrating 5.441 grams of vinegar. All right, let me break this down for you. Phenolphthalein is an indicator. There's a picture of it in your book. It turns pink in the presence of a base. It's clear in the presence of an acid. So we want to calculate the moles of acetic acid that are present in vinegar, and that is the acid that is in vinegar. As I said earlier, we're going to talk about acetic acid. We want to figure out how many grams of acetic acid are present in that 5.441 gram sample of vinegar. And we want to find the percent of acetic acid in vinegar. We can find all of these things from this titration problem. So let's look at the moles of acetic acid. First, we need to balance a neutralization reaction. So we have acetic acid, which is in our vinegar, acetic acid, and it's reacting with lye. This is our standard, right? So if we go back and look, we have NaOH. This is our standard. This would be our analyte, the thing that we are analyzing. So when we react those two things, we know we're going to form water, and we know we're going to make a salt from sodium and acetate. Acetate is -1, sodium is +1. So there's our salt, and there's our water. The second thing we need to do is figure out how many moles of sodium were used. So the problem tells us we have 30.84 milliliters. And we know that there are 1,000 milliliters in a mole, or sorry, 1,000 milliliters in a liter, and we want to convert our milliliters to moles using the molarity. So the problem gave us the molarity, so we do that calculation, and we get 0.00395 moles of sodium hydroxide. So if we know the moles of the base, and we have a balanced equation, which in this case it's all ones, then we can figure out the moles of acetic acid. And in this case, it's the same thing. So the first question asks us to find moles of acetic acid, and we found it. Pretty simple. Now let's find grams of acetic acid. Well, we have moles, so we just look up the molar mass of acetic acid, and we convert moles to grams, and we get 0.237 grams of acetic acid in our vinegar. So what percent of acetic acid is in vinegar? Well, we know percent is part over whole times 100. So we take the 0.237 grams part that we found. We divide it by the whole sample, which was 5.441 in the problem. We multiply it by 100. That tells us that in vinegar, there is 4.36% acid, which means you have 93 and something percent water, right? Very diluted. And there we go. Now, the last thing we're going to look at is a net ionic equation. I'm going to introduce this to you so that you've seen it. I'm not going to ask you anything other than vocab about net ionic equations, but I want to expose it to you because if you're in honors chemistry, you may end up taking AP chemistry, and we do cover net ionic equations in a little more depth in AP. So net ionic equations and acids and bases are pretty useful things to kind of combine together and look at. So let's finish up these last two slides by looking at net ionic equations. So we need to write a molecular formula for all the chemicals in our equation. We need to balance the equation. And then we're going to rewrite that balanced equation with all the ionic compounds that have changed. We're going to leave out solids. We're going to leave out and we're going to include our strong electrolytes in their dissociated form. We're going to get rid of what we call the spectator ions, all right? And that's going to leave us with a net ionic equation. When we do that, particles and charges are going to be balanced. That's a pretty big deal. You might be wondering, how do I know What is a solid? Well, I use the solubility rules that I learned earlier in the year when we talked about solutions, okay? So let's do a practice problem with that. Silver nitrate and sulfuric acid form silver sulfate and nitric acid. So what's our molecular equation? Well, silver nitrate is AgNO3. How do I know that? Well, Ag is +1, nitrate, NO3 -1. So when I cross the charges, I get 1s. Sulfuric acid, I know it starts with an H because it's an acid. I have H +1. Sulfuric comes from sulfate, SO4 -2. So when I cross my charges, I get H2SO4. Silver sulfate, right, because this reaction is going to be a double displacement reaction. I'm going to get silver sulfate, so I know I have Ag +1, and I have SO4 -2. So when I drop my 2 down, that 2 is going to go there, just like it did here. I'm going to get a 1 on the other side, and I'm left with H and NO3, and we know that H is +1 and NO3 is -1. Now, I need to balance this. So 2 right there. So let's balance it by let's do grouping. So I have 2 silvers on the right, so I need to have 2 silvers on the left. So I put a 2. That gives me 2 nitrates. So I need 2 nitrates. If I have 2 on the left, I need 2 nitrate groups on the right. So I need a 2 right there. That gives me 2 hydrogens. I look back to the left. Hey, I have 2 hydrogens, so that's good. I have 1 sulfate hooked to it. I have 1 sulfate on the right. So everything else is a 1. So that's balancing by grouping, which we've done before. And so now let's break this into our ionic equation. And in order to do that, I have to know who's going to break down and who's not. So we know from our solubility rules that all nitrates are soluble. So they're going to break apart into Ag plus and 2NO3 minus, right? So this is dissociation. I know that H2SO4 is a strong acid. How do I know that? Well, 4 minus 2 is 2. And for oxyacids, if it's greater than or equal to 2, it's a strong acid. And the definition of a strong acid is it will dissociate completely. So it has dissociated. Silver sulfate is an insoluble compound according to my solubility rules. So I can't break it apart because it's insoluble. And nitric acid is obviously soluble for 2 reasons. Number 1, I know all nitrates are soluble. And if I wanted to look at it from an acid standpoint, I have 3 oxygens minus 1 hydrogen, so that's 2. And any of our oxyacids that are 2 or greater are strong acids, and strong acids totally dissociate. Now, the next thing I want to do is I want to eliminate my spectator ions. So a spectator ion does not change from the left side of the equation to the right side. So who doesn't change? Well, nitrate doesn't change, and hydrogen doesn't change. But the thing is, on the left side, I only have 1 hydrogen, and on the right side, I have 2 hydrogens. So I can eliminate that whole hydrogen right there, but I can't eliminate that hydrogen. So I get rid of the 2. So now let's write our net ionic equation. What's remaining? What's left? Well, 2 silvers, 2 silver positive ions, right? 2 Ag plus 1 HSO4 minus gives me Ag2SO4 and H plus. And I would write a solid right here, and I would write aqueous, aqueous, and aqueous. And that would be my net ionic equation. There we go. Let's try one more, all right? Instead of walking you through this one like I just now did, I'm just going to kind of move through it. I'm not going to ask you to write one of these. I want you to see it. I want you to be able to spot a spectator ion if I give you a molecular equation. I want you to be able to explain it to me. But in this chemistry class, I'm not going to ask you to write one. Let's look at 10. So here's my molecular equation. So take a minute, go through, and make sure you can write that thing. We need to balance it. So we're going to balance it by grouping. We only end up needing 1, 2 right there. It's a pretty simple thing to balance. Our net ion equation we write by figuring out who will dissolve and who won't. So for the most part, everything will dissolve except my lead compound here. All right, so that's my solid, that's my precipitant. Now we go through and figure out who doesn't change. Well, my nitrates don't change, all right, because I have 4 on the left and I have 4 on the right. Everything else is changing. So my net ionic equation looks like this. These guys I've marked out. These are spectators. All right. And everybody else is part of the net ionic equation. Right? Again, I know we didn't have it on here, but I would like to see solid, aqueous, or whatever. Now, I'm not going to ask you to write one of these on a test. That is what I mean when I say I'm not going to ask you to write one of these. I'm not going to assume you can do that. However, right, that being said, we may write some of these if we are in person. Now, I'm making this video when we're still virtual. If we are in person, we may write some in class. But again, in first year chemistry, I do not ask you guys to write one of these on a test. So you won't have to worry about that. Just make sure that you can identify the spectator ions, and you know the difference between the net ionic equation, which has no spectators, the ionic equation, which has all of the spectators, all of the non-spectators, everybody is broken apart if they will break apart in solution, and a molecular equation. So make sure you know the difference in the three. Here's one more for you to look at to kind of give you some practice, all right? There we go. And that's it. So I know that was a long video, all right? Go back, watch the pieces you need, okay? I try to keep everything together so you wouldn't have a bunch of little videos to look through. If you have questions, please reach out. I would love to help you. Send me an email, send me a message on Remind, or just, shoot me a question. So if I can help you, let me know.